Uh, Good evening. Welcome to any newcomers, and welcome back those of you who were here for the first talk in this series 2 weeks ago. Is this about a good loudness? Can you hear me? Okay? All right, thank you. Remember that after the talk, there'll be a reception with refreshments in the dining area, which is over that way and downstairs. Tonight's speaker is Fernando Rodriguez-Villegas. Fernando was born and grew up in Argentina. He began his studies at the University of Buenos Aires in engineering, but soon realized that his true interest was mathematics and switched to the math department at the other side of town. There he began taking courses in analysis, which is natural for one coming from engineering. But before long he found his true love was in algebra and number theory classes. Her name was Adriana Sofer. This worked out very well. By studying number theory, which turned out to be the area of math he liked best, he also had the opportunity to woo Adriana. She's now his wife and is a research lecturer here in math at UT. They have two lovely young daughters who declined to come tonight, fearing that talk might be boring. Although their first grader wondered whether a knowledge of subtraction might enable her to understand something. I seem to have forgotten to say that Fernando is an associate professor here in the math department at UT. Anyway, he finished his undergraduate work specializing in number theory, and since Argentina was not too strong in number theory research, he went abroad for graduate work to Ohio State University, where he wrote quite independently a really outstanding PhD thesis in an area which is very close to the subject of tonight's talk. Fernando spent several postdoc years at the Institute for Advanced Study in Princeton, the Max Planck Institute in Germany, and at Princeton University. He has held both Guggenheim and Sloan fellowships. We're very fortunate to have him here at UT. He continues to do outstanding research, both theoretical and computational, and he loves to teach at all levels. He first taught at his high school to support himself at the university. Over the years, he has returned to Argentina several times as a visiting professor and to teach courses as a visiting professor, and has recently attracted excellent graduate students to UT. He's certainly doing his part to further President Faulkner's aim of strengthening the UT's relations with Latin America. Like Cameron Gordon, our speaker 2 weeks ago, Fernando plays the guitar. And he has recently been having fun playing the cuatro, a 4-stringed guitar-type instrument which he got when he taught a short course at a meeting held in the mountains of Venezuela, where the instrument is played. Another hobby of Fernando's is the history of mathematics. He has an exceptional knowledge of 19th century math in particular. Tonight he will tell us about the conjecture of Birch and Swinnterton-Dyer, and perhaps something of the long history leading up to it. Fernando.
I want to thank you all for coming, and also thank on has worked on elliptic curves, among many other things. To give you an idea of the deepness of John's work, let me mention the following things that are standard notation for several things in the theory of elliptic curves. The Tate algorithm, the Tate curve, the Tate-Safarevich group, the Tate module, the Castle-Tate sparing, the Néron-Tate height, the Serre-Tate canonical lift, the Tate-Poitou duality. And this is only for elliptic curves that his name is associated to. So with my colleague Volok over here, Felipe Volok, we came up with another Tate notation, which is the Tate index of a talk, which is how long it takes before the speaker mentions Tate's name. So this talk is about elliptic curves and especially rational points on elliptic curves. So this is a Diophantine problem. So what does that mean? Yes, I skipped one first thing I should say. Now you see the picture. But the very first thing one should know about the Birch-Swinnterton-Dyer conjecture is that it was made by two people. So Swinnterton-Dyer is the person on the right. And this is both of them at Birch's wedding. So Diophantus lived around the year 300, and he wrote a book called Arithmetica, and it's all about problems that have to do with equations that we want to solve with integers. And here's the famous, the page where Fermat made his famous marginal note. It's impossible to talk about Diophantine problems without mentioning Fermat. Now, the picture is kind of blurry, so you can't quite see, although, in fact, if we could see, it would be still pretty hard, because it's in Latin, and this second column is in Greek. But what it says somewhat over there, question number 8, and it says something, I'll come back to it, quadratorum dividere in due quadratus, something like that. And it's the question of writing a square as a sum of the squares of two other numbers. And Fermat, inspired by this, made this famous comment that he had a proof that there were no other solutions if we, instead of squares, had cubes and fourth powers and so forth. And he said he had a proof, but the margin was too small to fit. And so everybody wonders since what he had in mind. And it wasn't until recently that this theorem was actually proved. So Fermat lived in the 1600s and was a lawyer, and I understand he never actually wrote any mathematical text, but rather he made comments on his own copy of the book of Diophantus, and those marginal comments were incorporated in later editions of the book, of which we saw a copy. Now here's Fermat's last theorem. And it says, in a synthetical way here, that there are no integers x, y, and z, not 0, such that add up in this form, where the exponent n is 3 or more. And this was proved recently, as I'm sure you must have heard, by Andrew Wiles. And here's the paper of Andrew Wiles, the first page. Now, one thing that you may want to notice is that it has the word elliptic curves in it. And there you see written in somewhat readable form the comment of Fermat. And you see something about cubes into 2 cubes and fourth powers into fourth powers and so on, and the fact that the margin was too small. Now, let me mention, I was looking for things to bring for the talk, and I came upon this statement of Castles, who was another person who worked extensively in Diophantine problems, in particular elliptic curves. So let's read it. The study of Diophantine equation, that is the solution of equations in integers, or alternatively in rationals, is as old as mathematics itself. And it has exercised a fascination throughout the centuries, and the number of isolated results is immense. Some more or less general techniques and theories have been developed, and there are some grandiose conjectures. But the body of knowledge is less systematic than that in more recently established branches of mathematics, because we are concerned with the most basic and intractable mathematical material, the rational integers. And for me, that really summarizes a whole lot that the feeling about what it is that's going on with Diophantine equations. So for me, things that I would like to emphasize on this paragraph is the fascination, for one, and then the basic and intractability of what we're talking about. So the integers are both basic and perhaps because of that, intractable. And so things that we're trying to do with Diophantine equations are involve things where we only involve the integers, and perhaps because of that is because they're so complicated. Now, I tried to find a picture of Castles for you to see, and so I went to his webpage, and I couldn't resist bringing it up to you. This is Castles' webpage. Now, so we'll start doing a little bit of mathematics soon, but again, came upon this phrase of Henri Poincaré, who some of you must have, those who were here last time, heard about. Is the same Poincaré of the conjecture of the previous talk, and he wrote a paper on Diophantine equation, the number theory, around 1900, which is something quite remarkable given the fact that for many of you who may have known Poincaré before, you probably may know him from his work in physics, in geometry, and so on, and you may not know he wrote a paper in number theory, which is quite an interesting one. So he says something, I'm not sure I can translate this French phrase exactly, but I'll try. He says something like, when I try to sort of restrain myself, I found myself in the dark. I prefer rather to be taken as somebody who talks too much. And I felt that that was something I could use for my talk. All right, so let's go back to this problem of Diophantus, problem number 8 in book 3. Quadratum dividere in duos quadratus. So we want a number, integers a, b, and c, such that the square of a plus the square of b is the square of c. And this should remind you of Pythagoras' theorem. In fact, this is a very old type of question that goes indeed back to Pythagoras. And such solutions go by the name of Pythagorean triples. And here in this stamp from Greece, you can see a solution which you probably know already. That is 3 squared plus 4 squared is equal to 5 squared. Okay, so what I want to do is show you how we can completely solve this equation. So in a way, this is a success story for Diophantine equations. We will be able to completely give all solutions. So there's nothing left to be desired about whether we can solve this equation and what the solutions are and so forth. And again, looking for inspiration, I want to bring Gauss, who was another one of the greatest number theorists of all time. So what are we going to do to solve this equation? Well, the first thing that we do is we look at this a squared plus b squared equal to c squared, and we divide through by c. So say c is not 0. And let's call them x and y, the ratios of a and c and b and c. So a more familiar type notation. So what we have is the equation of a circle if we think of this geometrically. That is, if we think of the solutions to this equation were real numbers x and y, then what we see is a circle. So here's what we can do to solve the equation where now x and y are rational numbers. We start with the solution that we have, or that we can spot, namely 1, 0 will be a solution of x squared plus y squared equals to 1 with rational numbers. And then suppose we have this other solution x, y. Well, we draw the line that joins these 2 points, and what we see is that we get a line which has a certain slope. We're going to move, the line always will go through this point, so the only thing that can vary is its slope. And what I'll show you in a second that we can work out easily what that slope is. And the point is that the slope is going to be a rational number if x and y are themselves rational numbers. And so we can turn this around and say, well, if we have a line with a rational slope t, then we can find where is it that intersects the circle. And it will give us some point x, y, which will also have rational coordinates. And in this form, we have a correspondence, a one-to-one correspondence between the pairs x, y, and t. Well, except for one minor detail, which is that if the point x, y happens to be the point 1, 0 itself, then the line is a vertical line, in which case we'll think of the slope as being infinite. But with that proviso, we can give all the solutions in terms of the slopes. So let's do the math, as they say. So let's see how it goes. We have the equation of the line, and we can write it with the t as the slope. We plug it into the equation of the circle. We rearrange, bring the 1 to the left side, divide by x minus 1. X will not, eventually x will not be 1. We want to find a new point. And then we solve for x and y. And so we get an algebraic one-to-one correspondence between the pairs of rational solutions x, y to our equation and the slopes t, rational as well. Okay, so that's essentially it. That one could, if we really wanted to go back and go to the a, the b, and the c, we will have to work a little bit. But this is essentially the whole story for this equation. So let's turn off to a different type of equation. This is the type of thing that is very, very classical. Things like squares, cubes, fourth powers. Very quickly, once you look at simple numbers like squares, you ask questions like this. Well, what are the numbers which we can write as the sum of the squares of two others? Okay, well, let's have a look. The squares are the numbers 1, 4, 9, 16, 25, and so on. This is the number, so if you think of a little square with dots, that will be the number of squares, a number of dots in a square of side 1, 2, 3, 4, 5, etc. So let's look at numbers that are sums of two squares. Well, if we can list them. We can just go through the squares and add them and see what numbers we get. So here's the beginning of the list of all those numbers which are sums of two squares. So 2 is 1 plus 1, 5 is 1 plus 4, and so on. So for example, from here we see that the question of whether 7 is a sum of two squares, we can answer as no, 7 is not. Okay? Now, so this, what we're doing is using size, if you like. So if we give ourselves a number, if we want to ask whether it's the sum of two squares, we can run through this process and just check. There's finally many checks that we have to do and then figure out whether it is or not. Now, that's not going to take us too far, because the number, we could have a number that is huge. So for example, the number 10 to the 10 to the 10 plus 3 is not a sum of two squares. Okay? And we'll see that in a second. Now, you probably don't want to go about checking all the numbers that are smaller than this to see if you can work it out as a sum of two squares and then figure out you can't. So we need something else. Size is not going to do us that much of a good. Okay, so what is it that we can do? What other techniques do we have in Diophantine equations? Well, what I thought of saying at some point is that essentially the problems of Diophantine equations can be so insanely difficult that you use absolutely anything you can get your hands on. Okay? So we use a bit of geometry, and what else can we use? Well, there's a very basic technique which is using modular arithmetic. Okay? So I wanted to show you that. Some of you might be familiar with it. I'm sure there would be. But I'm going to do this assuming that you have not seen it. Or be a review if you have. All right, so now at this point, I thought I would do a little survey. So how many of you, who of you have ever heard of a slide ruler? That's pretty good. How many of you actually used a slide ruler? Okay. Now, so here it is. This is a slide ruler for modular arithmetic. Okay, so what do I mean by modular arithmetic? Well, if you think of the integers 0, 1, 2, 3, and so on, and -1, -2, they form a line. Okay? Now what I want to do is wrap this line around in a circle. Okay? And the thing is that you can work with these numbers in a circle. You can add them, you can multiply and subtract. Divide becomes a bit of more of an issue, but you can operate them, so it becomes a new arithmetic. Okay, so here's an example with 17. So here the numbers are wrapped around in a 17, a cycle of 17. So you go 0, 1, 2, 3, 4, and when you go to 17, it's the same as 0. So 18 is the same as 1, 19 is the same as 2, and so on. You wrap them around. Okay, so this is a slide ruler for numbers mod 17. So addition is going to be rather simple, but let's say for example we want to sum 9 plus 9 plus 13. Okay, the numbers are sufficiently small, I'm sure you can do it in your heads, but anyway, this will do it too. So what do? We put the little blue circle in the 9, so that means 0 plus 9, 9 plus 0 is 9. So all these pairs are now in this same situation. So 13 plus 9 is 5. Okay? And what does that mean? It means that if you add 13 to 9, you get 22. So if you wrap it around the circle, it will be the same as 5. Okay? It gets more interesting to do multiplication. So let's switch to multiplication. And the thing is that we also have a slide ruler. And now this, the theory behind the fact that this actually works requires knowing a little more than just what I said. But it does work. So if we want to multiply, it's the same principle, and it's the principle of the slide ruler for those who are familiar with it. So for example, let's say we want to multiply 13. So we put the blue over here in 13. And then let's say we want to multiply by 11. So 11 times 13 is 7. Okay? And now that calculation I don't think I can do right here in my head. But what does that mean? It means you take the number 13, you multiply by the number 11, it gives you some 3-digit number, and you wrap it around the circle and you see where it lands. So in other words, you cast out all multiples of 17. Okay? All right, so that's modular arithmetic. And I want to show you how is it that one can use this modular arithmetic to prove or mostly disprove the existence of solutions to equations of the sort we're talking about. So let's go back to this example. So why is it that this number is not a sum of two squares? That's what I'm claiming. Well, let me show you why. One way to do this is to look at this fact modulo 4. Modulo is the name we gave to this arithmetic. Modulo 4 means we do things on a circle with 4 things. So we wrap around every 4. So let's look at what the sums of two squares look like if we look at them modulo 4. Well, the squares are 1, 9, 16, and so on. If you look at them, you'll see that if you wrap them around the circle every 4, they always come out to be either 0 or 1. Okay? So this whole string of numbers, when viewed in a circle, they always land in the same place, either 0 or 1. So, for example, they skip 3. Okay, they skip 2. All right, so those are the squares. So now let's look at the sum of two squares. Well, this arithmetic works in the expected manner. So if we look at a number which is a sum of two squares, you'll have two squares to add, right here. Well, one of the squares could be 0, the other one could be 0, in which case the sum of two squares is 0. Or one of them could be 1 and the other one 0, in which case the sum is 1. Or both could be 1, in which case the sum is 2. And there's one guy conspicuously missing. 3 is not in the list. 3 is not a sum of two squares modulo 4. So if we go back to our huge number over here, the thing to notice is that this huge number, if you were to wrap it around the circle every 4, it will end up at 3. And the reason is that we have 3, so we do 3 little steps, and then the rest of the steps is a multiple of 4. So every time you do it, you'll always come back to the same place. So that shows that this number is not a sum of two squares. And for that, we did not use size. We used something else. We used arithmetic modulo some number. In this case, modulo 4. Okay, so this is then a very basic principle in arithmetic, that we have this extra new arithmetics to use. So we have a problem that we want to solve in integers. We can try to see if something like this will hold, where we look at the same equation modulo some number, and somehow we can tell whether there are solutions or not. Okay, so right, so the conclusion of our discussion is in fact not only just that big number that we had over there, but any number congruent to 3 mod 4 will not be a sum of two squares. So in other words, that is a negative answer to a particular Diophantine equation. Now, so the key questions in this context are, well, what information about a Diophantine equation that is reduction modulo every number carry? So, for example, we can ask ourselves the question, well, what about in a positive sense? What if we have an equation, we look at it modulo every single possible number that you can think of, and it has a solution? Then what do? You have not disproved that the original equation does not have a solution. Sorry, they have not disproved that it has. Can you say, well, if it has a solution modulo every possible number, can we say that then it will have one with integers? Well, unfortunately, no in this generality. Okay? But still the question is, what information about the original problem does the equation modulo numbers have? And also, how do we retrieve this information? So there's a success story here too. If we have, let me just say it in a sort of simplified manner, but if you have an equation which is essentially involving only squares, then this principle the Hasse principle that I'll now explain in more detail works. So what is this principle? In number theory, when we look at things modulo numbers, or especially modulo prime numbers, we call that looking at the situation locally. And in a way that I will not attempt to explain, this geometrical feeling to the word locally actually has a relevance. So primes, in an appropriate sense, are points. And what we're looking at when we do modulo a prime, we're studying the situation around that point. So the local is not just a random word. And the global is what we will actually want to solve. For example, is a number the sum of two squares? That would be the global question. The local question will be, can we try to solve that equation modulo numbers? Okay, so the success story is that, as I was trying to say earlier, if you have equations that involve only squares, then it is true that if the equation has a solution modulo every single possible number, then in fact it does have a solution over the rational numbers. So there is such a principle, a local, a global. And let me remind you that in this problem that we said over here, we had the advantage of having one solution to get going. Okay? So what we did is we solved completely the equation by starting with one solution and drawing lines. But we need that point to get going. And so the first question if we have an equation of this sort will be, well, can we tell whether we have a point to get going? And this principle of doing things locally for equations with squares only, it works. But unfortunately, it stops working very soon. Any equation that has involved powers that are more than squares will typically fail. All right, so now we come to finally to the topic of the talk proper, which is elliptic curves. Okay, so let me give you the definition sort of in a mathematical way, and let's try to get it clear what it is. So for us, an elliptic curve, E, is an equation given in this form. So you have two variables, x and y. The a and the b are constants. We'll think of them as integers. And the equation is y squared equals to x cubed plus ax plus b. So it's a polynomial of degree 3 in x. And there's one proviso that we want the right-hand side of the equation, which is a polynomial of degree 3, to have distinct roots. Okay? So roots as complex numbers. The polynomial has degree 3, so with multiplicity it has 3 roots. We want all of those roots to be different. Now, we talked about the equation x squared plus y squared equals to 1. We looked at the real solutions. That forms a circle. Now we can ask the same question here. If we look at the solutions of this equation, where x and y are real, what are we going to see? Well, this is one possible thing that we can see. Okay? In this case, the cubic, the right-hand side of the equation, has only one real root, which is right there, and the two other roots will be complex, so we don't see them here in this picture. Or it could also happen that the cubic has 3 real roots, in which case you will see these 3 real roots there, where it meets the x-axis. And the equation, recall, had a y squared equals something. So if you flip the y and the minus y, you go from one point of the curve to another. So the curve has this symmetrical form. Now, we could also talk about the solutions of these equations with complex numbers. If we did that with the equation of the sum of two squares, x squared plus y squared equals to 1, then that's a circle if we look at the real solutions. But if we look at the complex solutions, we get actually a sphere. Okay. Now, so what do we get if we look at the solutions of an equation like this, of an elliptic curve? Well, if you were here earlier, you've probably seen some of those pictures in the slides. And I thought I would bring you a real-life elliptic curve, since there was this question last time whether math really exists or is an invention. So I looked around at home and found my own elliptic curve. There were, my daughter, I don't think, will miss it anymore. So here it is. So those are the complex solutions to an equation of the form that we wrote. Although, of course, it does require some doing to show that indeed that's the shape. So now let's try the geometry. It worked for us on the circle. What will it give us if we do some geometry with an equation of this sort? Well, if we draw a line, what will happen? Well, for example, in the first case, we have this picture. Because the equation is of degree 3, it's a cubic, when you draw a line, it will meet this cubic in 3 points. Okay? So that means that even if we have 1 point and we wanted to play this trick of drawing lines to get all the other points, we have a bit of a problem. Because if we fix one of the points, then when you try to find the others in the intersection, you don't get 1, you get 2. But that's, in a way, it's even better. Because what is it that we can do? Let me show you the case with the little blob there. Well, we can turn this into our advantage and do as follows. Let's suppose we have 2 points, this one and this one. And we draw the line that goes through them, and it will meet this cubic in some other point. Okay? So what we have is something that, given 2 points on this curve, we produce a third point on the curve. Okay? So 2 points give you another point. Now that starts to sound like something pretty good. Now, there's also a remark that if these 2 points happen to have rational coordinates, so coordinates x and y, which are rational numbers, then when you draw the line and do the algebra as we did in the case of the circle, which I won't write down, and you solve for what the other point is, you will realize that because the original 2 points have rational coordinates, the third one will also have rational coordinates. Essentially what happens is we have a degree 3 equation here, and 2 of its solutions are rational, and therefore what we really have is a degree 1 equation, which will also have a rational solution. So in other words, right now what we have is that given 2 points with rational solutions, we can produce a third point with rational solutions. And so what happens is that we can take this and make it into an operation which is very much like adding. So what I'll show you in a second that this operation will turn the points on the elliptic curve into a group, which means that you can take 2 points and add them and produce a third point in a systematic way where you will have associative law, inverses, and it will work just the same in this structural sense as if you were adding numbers. All right, so I'll show you how we can do that. Okay, I don't know how much you can see from that. So this is a little interactive thing for adding points. So here you see the equation. It's -7 and 2. So before I add the points, let me show you something which I think is really neat. That we can move the slider and we'll see how the shape of the curve changes. Okay? So if we do this, at some point you get something interesting. Suddenly this blob met the other part. And so what happened is that this thing is not technically an elliptic curve anymore. Because what happened is that those 3 roots that were distinct, suddenly 2 of them became the same. And if we look at the picture in this complex sense, what happens is that basically what we did is sort of pinch this thing like this. And really it went from being a torus to being a sphere. So in a way we're back, essentially back to the circle case. So that's a sort of the generate situation, but if we move some more, we get out of it, and you see how the blob disappeared, and now it goes back to being one little piece alone. Okay? So let's go back to the blob. So how do we add 2 points? Well, the idea is already basically mentioned, but there's a little twist to it. So let me put a point there, and then let's find another point. And you see this little button on the top, which tells us that we can add them, P plus Q. And what is that? The thing is as follows. We draw the line that joins P with Q. It meets the curve in some other point. And now that is not quite it yet, but we'll reflect down that point, flip it over, and that new point, R, we're going to declare it to be the sum of P and Q. Okay? So what would be, for example, doubling a point? Well, we have 2 points. We can draw the line through them and do this operation. But if we have 2 points, well, what's the line through them? Well, the line through them now, what happens if you think of this is in a limiting case, if the 2 points, one is moving until it becomes the other, the line that goes through them will move over and become the tangent line. So if we had just 1 point, you can double it. And in this case, the double of this point meets the curve outside the screen, so we don't see what it is. So let me do another one. Let's say we double this point. Okay? So now we have something that is quite neat, which is that we have an operation on these points on the curve which form a group. Okay? Now this turns out to be, of course, extremely important and useful. And I'll come back to the usefulness in a little while. All right, so back to the modulos. Back to doing things modulo numbers. That turned out was useful before. Well, it will be useful again. Now, one thing that I mentioned in passing, let me come back to it. If we go back to our little slide ruler here, there's one thing that we may want to notice, is that in this situation, we can actually divide. Not only can we multiply, but we can divide. Okay? So, for example, what would be 1 over, so to speak, 9? Well, 1 over 9, whatever it is, it has to be something that if you multiply by 9, has to give you 1. So let's sort of work our way back. And this is the situation of multiplication by 9. So every pink number multiplied by 9 is the corresponding blue number. Okay? So what we should do is look for a number in the pink side which has the 1 on the blue side. Okay? And it's right there, 2. So 2 times 9 is 1. Well, 2 times 9 is 18. 18 modulo 17 is 1. If you wrap it around the circle, 18 will come back to 1. And you can see that every time, every number you pick, you will be able to figure out another one you can multiply by to get 1. So that means that now, in this situation, you can actually divide by every number, of course, other than 0. And this is a virtual of the fact that the number of points in the circle is a prime number. So 17 is a number which doesn't have any divisors other than 1 in itself. So the claim that I'm trying to make here is that if you do this with any number of points in a circle like this, but a number which is a prime number, you will be able to divide. And if you put a number which is not a prime number, you won't. Okay, so we'll stick to prime numbers because that is what, in a way, is the most similar to the usual type of arithmetic. Okay. So back to this. So we have our equation, for example, the elliptic curve. And all of the things that we talked about, adding points and drawing lines and so on, makes perfect sense modulo a prime number p. Because it's all algebraic. Although we're talking about geometry, we're drawing lines and we're putting points in a picture, if down in the bottom of it, it really is algebraic. You manipulate an equation, the equation of a line, and you put it into the equation of the curve and you solve. So, although we can have really very useful pictures modulo p, we can still do every single thing that we did before. So what we have is algebraic geometry modulo this prime number p. So in particular, you can add points modulo p. Okay? So you take your equation of the elliptic curve, you look at it modulo p now, and you have to be a little careful that your curve somehow modulo p doesn't become this pinched thing, okay, which is a bit of a technical point. But if we really have now a curve modulo p, then you can add points. Okay? And as I'll mention, that's actually a fantastically useful fact. Now, if you do geometry modulo a prime number p, you don't have pictures that are really useful. You know, the points are, there's a finite collection of solutions. X and Y run from 0 to p minus 1. So at most, there'll be p squared solutions to this equation. So we're talking about a collection of points. And there's no really useful way of putting them in a picture that you can use. But I like to think of the fact that if you look at something modulo p, pictures are replaced by counting. Okay? So one thing that we can do is count how many solutions there are. Okay, so we start with our elliptic curve with the a and the b integers. We pick a prime, like 17. Look at the equation modulo 17 and try to look for solutions x and y. And then we count them. We see how many there are. Well, I don't know how many it'll be. It'll depend on the curve, on the prime. Let's call that number n sub p. Okay? So the very first question is, how big can this number be? Well, x and y run between 0 and p minus 1, so certainly there's at most p squared such points. But that is kind of way off from the actual truth. What happens is that, well, let's talk about the circle. So for example, on the circle, how many points are there on the circle? Well, we have x squared plus y squared now congruent to 1 modulo p. Well, just as before, there are as many points as slopes. The same picture that we did for the slopes, we can do modulo p. And there's p plus 1 slopes. Any number from 0 to p minus 1 going around the circle. And then one extra number, this infinity slope, that we have to take into account. So if we look, the technical word would be this sort of projective line has p plus 1 points. Now, as it happens, an elliptic curve also has about the same number of points. Okay? So this is the theorem of Haas's, that if we look at NP, the error, so NP is roughly p plus 1, just as it was for the circle, with some error. So the difference between NP and p plus 1, if we think of that as an error, well, the error is not bigger than 2 root p. Now, if you think about it, root p is significantly smaller than p. So we can argue that the number of points on this elliptic curve is basically p plus 1. There's a little variation up and down possibly. But that variation doesn't go over 2 root p. So that's a very important theorem, which is part of the Weil conjectures, and which, in a way that I'll let you ponder, and hopefully you'll be encouraged to ask about, if you don't know, is related to Jeff Wahler's stock, which is the very last one in the series. I'll leave it as a little bit of a mystery for those who haven't seen it. All right, so what are we going to do with this reduction modulo p. Okay, so in particular, the elliptic curve has roughly p points. P plus 1, let's just forget the 1. It's about p. Okay? All right. So let's go back to this Hasse principle. We have this equation. We look at a modulo primes. And we try to collect some information that will lead us somewhere. And what turns out to be a useful thing to do, or what we're going to keep from this equation modulo p, is how many points it has. It has about p, but there's a little variation. So that variation should tell us something. So we go back finally to Birch and Swinnterton-Dyer. So what they did is the following. Okay, let's take our curve, reduce it modulo primes p. Let's count the number of solutions there are. There are about p. Okay. Well, so let's look at the density. Okay. So let's look at NP divided by p. All right. So that's sort of we'll measure how far off are we from being p, the number of points. Okay. And then in order to sort of try to retrieve the information, as I was saying earlier, they consider the product of these densities for primes from 2 to a given x. So you do this with 2, 3, 5, 7, and so on. And you go up to x, and you look at this product. So what's the idea? The idea somehow is the following. Suppose our equation has infinitely many rational solutions, the original equation. Okay? So their idea is that that should reflect itself in the number of points in P. And in which way? Well, it should reflect itself in the sense that NP will have to typically be larger than expected. Whereas if the equation originally has no solutions, then what we should expect is that this density should basically remain about, shouldn't be on average very big. It should be sort of on average about the same. So sort of vaguely, this is the intuition, and this is one way to try to capture that. And so what they did, and I find this is, for me, is great, is what they actually did is numerical experiments. So you take your equation, pick A and B, and now count the number of points, do this product, and look what the product looks like. And what they discovered is, what I was saying earlier, that it seemed to happen that every time that the curve E had infinitely many solutions in rational numbers, then this product P of x got bigger and bigger. Okay? Whereas if the equation had no solutions, or finally many solutions, then this product seemed to stay basically flat. Okay? So for the purpose of this talk, I did exactly that experiment with 2 elliptic curves, just to show you what this looks like in practice, if I can remember what key it is. This one. Okay, so here's the picture. I took the number of primes up to 20,000. Okay? So the primes go sort of that way. And then in here, I graphed the product that I had before. Okay? And this is 2 curves. This is a curve which has 5 points on it. Okay? So it's essentially flat. And this is a curve that actually has infinitely many points. Okay? So that's the type of evidence that Birch and Swinnterton-Dyer were looking at. And after amassing a bunch of examples of this sort, they realized that, well, something's going on here. And what should be going on is the conjecture. So in order to phrase this conjecture in a nicer, more neat form, let me introduce a technical thing, which is called the L function. Okay, so this elliptic curve will have associated to it this function, which we call the L function of the elliptic curve. Now, I like to think of this function as something like the DNA of the elliptic curve. It's sort of like the genome or something. I mean, we take this elliptic curve, we chop it off in these little local things, modulo prime, and then we put it all back together in one big string, which is this function. Okay? And now we had great hopes about this function. We expect this function to tell us a lot of things. Okay? About the curve. Now let me try to describe it, and I'll try to be non-technical as possible, so I'll just give it in this somewhat obscure, without giving all the details, obscure form. So the L function is a function of a variable s, and it's a product. It's a product over all primes of a certain thing here, fp of s to the minus 1. And these fp of s's are functions themselves of s that are associated to what's going on the curve modulo the prime p. And these functions go by the name of Euler factors, as Euler introduced them in the case of the Riemann-Zeta function, which again is the subject of just Waller's talk. Now, the only thing I want to say for the relevance of the conjecture is that whatever this is a function that if you put s equals to 1, it comes out to be exactly that number that we were talking about. Okay, that density, it measures how big somehow the elliptic curve is modulo that prime. All right, so now let's just think naively what's going to happen. Well, if we put s equals 1 in there, we get sort of the reverse. We get p over np. And what we were saying is that np over p, we take the product of them, should grow if the elliptic curve has infinitely many irrational points. So since they kind of go reverse in there, it will mean that this number would have to be 0. Unless, I mean, there's a bit of wishful manipulation in what I'm saying, because there's some analysis to do to sort of show that this is the correct thing. But intuitively, I think it should be clear that that's what it is. All right, so finally, we come back to the conjecture. And this is the conjecture in its most basic form. And it says the curve E has infinitely many rational points if and only if this magic L function vanishes at s equals to 1. And this indeed seems to be the case in numerous examples that one can work out numerically, where one can actually compute this number, check that it's 0, and correspondingly check that the equation of the elliptic curve has infinitely many solutions. Okay, so this is what I want, as far as I want to go into the elliptic curves and the Birch-Swinnterton-Dyer conjecture, but I thought I will also say something about something else I mentioned before, which is the fact that we have this elliptic curve modulo a prime number, that we can add them at points. And this turns out, as I said, extremely useful, in particular in cryptography. So I find this absolutely fascinating, that elliptic curves, you know, the conjecture of Birch-Swinnterton-Dyer was made in the 60s. At the time, my guess is that the general public will consider this fairly irrelevant or esoteric, or who knows. Now, I don't think the general public will think the same way. And I'll show you examples of that. Not exactly on the conjecture, but on the elliptic curves. And I find this really interesting. So let's see if this comes back. Okay, so here's RSA, a cryptography company. Okay? Has a tutorial on elliptic curves that you can find on the web. What are elliptic curves? And they tell you. National Institute of Standards and Technology. And this has a beautiful phrase down below that says, NIST recommends but does not require the following set of elliptic curves for federal government use. In fact, the situation is so strange that one thing that I have not mentioned is Anyway, there's certain type of elliptic curves that people are interested in, and some of the research on this is done under a defense contract. So at some point there was this very strange situation where there was announced that there was a curve with rank 25, whatever that means. Now the curve was not available because it was secret. So there was a delay of about like 2 weeks or something between the actual announcement of this existence of this curve and the actual public appearance of it. So things are really strange, I believe. And there's another one, which is cars. I don't know if you can see, there's a little yellow thing there, which you may recognize as the little things that you have in cards, telephone cards in Europe and other countries. Okay. So this is a company that programs these little chips for you. And yeah, as you must guess. Whoops, no, what that happened? Somewhere along the line down below, there's the word elliptical curves. I don't know if I'll be able to find it. Up. Anyway, the point to make is that suddenly all sorts of companies and situations, huh? Security, there we go. 160-bit elliptical curve cryptography for terminals and enhanced basic cards. So as I heard Alice Silverberg in a talk, she said, you know, we'll be carrying elliptic curves in our pockets pretty soon. And so they come in with cryptography, and I won't explain how the various ways that it could happen, but one of the things has to do with the fact that you can operate and add points on an elliptic curve. And in fact, it has to do with logarithms. So sort of like a slight ruler on points on an elliptic curve. But they also appear in a different way, which is that RSA company that I showed the page before has to do with the method of encryption, which is a very popular one. That method of encryption relies on the fact that one expects that factoring numbers is very hard. So if I take a 200-digit prime number and another 200-digit prime number and I multiply them together, we expect nobody else in the world to figure out what those prime numbers were. So, as it happens, again, elliptic curves provide one of the best known and efficient ways of factoring numbers. So it's really interesting how these elliptic curves suddenly are appearing in all sorts of contexts. And I think I'll stop here.
So are there any questions?
In the picture you showed, where it looked like the whatever it is, the product was climbing bigger and bigger. It looks logarithmic. Okay.
Let me guess. Are you a mathematician? Yeah. That's what I thought. Right. So the second chapter of the story, I think, maybe is what you're leading to.
I'm wondering if there's a refinement of the Birch-Swinnterton-Dyer conjecture. The logarithmic shape suggests that Dirichlet's density of primes. So I'm wondering if there's a refinement of the Birch-Swinnterton-Dyer conjecture that has to do with that.
All right, let me try to answer this in 2 minutes with a lot of technical terms in it. So, yes, indeed. So, the next thing you want to ask, if you can't prove the conjecture, is, well, what else can we conjecture? And what we conjecture is that the way this product grows tells us even more about the elliptic curve. So I just mentioned growing or not growing, but how it grows should tell us more. And what it tells us should tell us something about what's called the rank, which I briefly mentioned, the rank 25 example. The rank is the following. It's the theorem of Mordell and Weil that the number of the rational points on an elliptic curve form a group, we know that, but it's a finally generated group. Okay? So there's finally many points which you can use to generate all the others, all the other solutions, by this operation of adding and so on. And so the rank is how many generators for sort of the non-torsion part there are. So the bigger the rank, the more this product should grow in a very concrete way. Yeah.
One question, for the one kind of conjecture, there have been several attempts, most of them not, all of them not successful. But what about this problem? Are there some directions in which people are moving to solve it?
Yeah.
Well, I was just going to repeat the question that's asked. Are there some positive results on this conjecture?
Yeah, well, I'm glad you asked the question. Of course, it's a natural one, and people have been working very hard on this conjecture for many years, and there are indeed very striking positive results. The striking in the amount of technique and work that it involves. Now, maybe after I told you, it'll feel a little unsatisfactory. But so we know things, for example, if the L function, this value at 1, is not 0, then we know the curve has finally many points. And we also know that, well, there's one other case where we know also exactly that, in fact, that the rank is 1. So it gets a little technical to explain, but there are two very sort of major works that prove parts of this conjecture, mostly when the rank is 0 or 1. But nothing is known, as far as I know, for a rank bigger than 1.
Well, if there are no more questions, let's thank the speaker again and have some refreshment.